everyone. I hope you all are doing well, and I hope your families are keeping well as well. It's been a tough couple of months for everyone, and even though the situation is better, I still hope that everyone's keeping safe at it. It's really nice to have you all here in person now. Uh, I hope I hope most of you also saw the first session, the first virtual session that we had that was streamed on YouTube a few days ago. If you haven't, that's also all right. I'll just recommend that you do check it out at some point next couple of days, so you'll be able to catch up and understand what we'll be talking about today in more detail. And in any case, we'll do a little brief for everyone, so you'll have a general idea, hopefully. So just an introduction once again. This program is called the Fundamentals of Particle Physics, and Uday and I'm accompanied by Devangi and Pantho, and together we're trying to teach you guys the basics, which is what the word fundamental applies, of the field of particle physics, which is one of the most interesting and relevant fields in physics right now. And I'm sure you are interested in the field to some extent. That's why you registered for the program. And I'm really glad to see that so many of you decided to attend this live session as well, because I think online learning is definitely has proven to be, other than watching a live stream, at least being in a live session on a live conference I think that makes a lot of difference. So really glad to have everyone here right now. So before we do a recap, Pantho, Devangi, do you want to add anything?
I would like to add, if any time while we are speaking or teaching something, if you guys have any question, please raise your hand or unmute yourself and ask a question.
Yep. So that's something you can always do. Don't hesitate. That's the point of having the session. So I guess I'll present my screen right now, so you guys can see some slides that we prepared for you. Oh wait, give me a second. All right. Is my screen visible? Can someone confirm that?
Yeah, it's visible.
All right. Right. So we'll do a very brief recap of what we covered in the last session. So the last session was a brief introduction to particle physics. We talked about the history of the atomic model or the atomic theory, and we came to and we introduced you guys to the standard model. So the reason why we discussed the atom first, because the idea behind particle physics is to reach the smallest scales possible, right? So the reason why people are invested in doing research in this field is that they want to see what the universe is made of. They want to see if we break everything down to its core elements, like if we keep breaking it down, what do we get? At what point does something become indivisible? And that's what this field is really about. And that all started from the atom. So the idea of atom, as we discussed in the previous class, stemmed from ancient Greek philosophy and ancient Indian philosophy. And after, in the more modern era, it became more scientific. And we came up with a lot of different models of atomic theory, some of which are the Rutherford model and the Thomson model, which you can, again, you can watch that in detail. You can learn about that in detail by watching the session, which is still on YouTube. And at the end, we came to the conclusion of, by accepting the current model of an atom, which was known as the electron cloud model. And at the end, what we basically discussed was that how the curiosity of scientists propelled them to further investigate this field, right? So even after they had designed the idea of an atom, and even after they had constructed an understanding of what an atom is and what everything around us is made of, they still wanted to go further. They wanted to know whether the atom and the protons and electrons, which are the components of an atom, they wanted to know whether these are the true components of everything, or could they be divided as well? This was the curiosity that they had. First, they thought that atom was the smallest possible smallest thing possible in the universe. But then they decided to investigate further, and to their surprise, they unlocked a new different field of physics, which is known as particle physics, where they started discovering what now called fundamentals. So fundamental particles basically mean particles that have specific properties which are fundamental, which means that they are not made up of anything else. They are indivisible in the truest sense. And that is what particle physics is really about. So that is what we study in particle physics. We are trying to study the properties of these different particles. We're trying to study how these particles interact with each other, how they get combined, how they react, and we're trying to form an understanding of the universe based on this investigation at the smallest scale. So at the end, we discussed the standard model of particle physics, which is basically a theory that explains all the particles that exist and that we have discovered as of now. So the standard model is this table. I'm sorry. Oh yeah, here it is. So I'll go back to the previous slide later on. But this is the standard model. I'm sorry, it was supposed to be on the first slide. So it contains all the fundamental particles that we have discovered up till now. So it's not just a table, it's a theory, because the standard model is basically saying that everything that we know around us is made up of these particles, and it's a theory. We don't know if it's completely true. We don't know if it's complete as well. We don't know if we have discovered all the particles, but that is the current state of the standard model right now. That's how we look at the universe as of the moment. So why do we study the standard model? Why is it relevant? There's a couple of reasons why. So first of all, there are these four fundamental forces in the universe. As we go on in this session only, Panthu will explain this further. But these four fundamental forces are forces that govern everything in the universe, which will, again, as I mentioned, we'll go into the details of that. They basically govern everything that happens in the universe. And the standard model allows us to explain those things. The standard model allows us to find out how the particles are connected to these fundamental forces, and it also explains how these fundamental forces interact. So an example of that is, you might have heard of this force called friction, right? So if I take this cube right here and if I slide it across my hand, it's experiencing some friction right now, right? And if I ask you, how is my hand exerting friction on this cube, you would say, oh, because of certain roughness in my hand, or you may say because of the molecules that are interacting between my hand and the molecules of this cube. And you may have explanations like these, right? So that's how the force of friction is interacting, right? And because it's dependent on what my hand and this cube are made up of, the molecules and everything that makes my hand what it is, and that is how friction comes into existence. In a similar way, at the smallest possible scales, we also wanted to figure out how these fundamental forces are interacting with each other, right? We wanted to figure out how these fundamental forces are acting on each other. And we explain that by using the standard model. We explain that by uh, thinking of these different particles as carriers of these different forces that make it possible for these different forces to act on different particles, different objects, and so on. We'll go into the details. Then another reason why the standard model is so important is
Voice is not coming.
Um,
Can't hear you.
Uday, I guess he had some internet issue.
Yeah. So you can continue, Devangi or Pantho, anyone?
Yeah, okay. I'll share the screen and then we can continue.
Yeah, Uday, we can now will you please speak?
Hello,
Yeah.
Uday?
can you hear me?
Yeah,
Yeah.
yeah. Now we can hear you.
All right. Yeah, I think I got disconnected for some reason. Sorry about that. Can you see my screen as well?
Yeah, yeah.
Oh, all right. Should I continue?
Yes.
Okay, I
Go on.
guess I'll continue. Okay. Yes. So I was saying that the standard model allows us to make predictions. So as I mentioned earlier, we don't know if the standard model is complete yet. That's why we call it a theory, right? A theory is something which scientists predict using their knowledge and using their logic, but we don't know if it's true for sure. So we don't know if the standard model is complete. However, by using some complicated math and physics in association, we can make some predictions about where different particles could exist in the standard model, and they often turn out to be true. For example, there are these fundamental particles known as the W and Z bosons, which had not been discovered yet, but there were some physicists who proposed the existence of these particles. They predicted these particles by looking at the standard model. And a few years later, scientists conducted some experiments, and it turned out that these particles actually existed, and they fell at the exact same spot that the physicists had predicted. So that's why the standard model is so strong and so important, because it allows us to make very good predictions about the future of particle physics. And as I mentioned earlier, the standard model also allows us to look at the future prospects, and it not only gives us a logical and a systematic view of the particles that we have discovered, but at the same time, it also gives us an understanding of what we can discover and what is yet to be seen by us. So I'll just do a quick recap of what we did in the last class. So there are four types of particles that are present in the standard model. These are called the quarks, leptons, gauge bosons, and scalar bosons. I'll go into the details of them later on. So quarks and leptons belong to a family of fundamental particles known as fermions, because they share certain properties that we go into later on. And then there are gauge bosons and scalar bosons, which are collectively called the elementary bosons. So the standard model is the overall model, this table that you see over here, which is divided into two sections, which are the fermions and the elementary bosons. And the fermions are divided further into quarks and leptons, and the elementary bosons are further divided into gauge bosons and scalar bosons. And that's how the standard model works. So before I go on, does anyone have any questions till this point? If not, we can go ahead then. So first, I'll start.
Just one sec. Can I just add one line here?
Yeah, of course.
Students, are you understanding that why the standard model and why this discussion what Uday is doing? Did you understand that how the particle physics right from root level and how it is developed and how the new scientific invention and discoveries were required? Are you understanding that? What was the requirement of all this? Why this is happening? Are you getting it? May I ask Urjit? Urjit is in the team. I can see Urjit.
Ma'am,
Yeah, louder.
hello, ma'am, am I audible?
Yes, bacha.
Ma'am, so we're studying the standard model and the basics of particle physics just to understand how our universe and what our universe is made of. And not only an atom, but how atom is made from much smaller constituents.
Okay. So can you connect this with like when you say universe? So are you understanding that how the universe or atom or electrons and protons, how these things were made? Are you understanding it?
Yes, ma'am.
Okay, is there anyone in this group who can explain me what Uday has just explained, except Urjit has already said? Is there anyone who can speak little bit about what Uday has told just now? Any one of you? Because see, why we did not go on YouTube, so that it can be interactive. Okay, so if you interact, it's good, Are you understanding what is bosons? What are fermions? A simple question. Need not necessary that whole module will, we are in a hurry to finish whole module. But if somebody can explain me what are fermions, I'll be very happy. Any one of you. Let's say Aishani, Nagpal, what are fermions? Yeah, can you speak up? So Uday, in that case, can you please explain? And when you are saying, about fermions and all, just.
You're asking everyone.
Yeah, I'm asking everyone.
Ma'am, for which complexity should I answer this one?
Your wish.
Like just definition or the spin, or I don't know in which way do you want the answer.
No, I just want what Uday has said just now. Has that made sense to you? That's what I'm asking. Have you understood what is fermion, Chaitanya? Yes, Chaitanya, go ahead. And if you are speaking, you are muted. So please unmute and speak. Okay, very simple questions to any one of you except Urjit. When we started, we, with kids, we're discussing about atom, proton, electron, neutron. Why was it required that we went further? Why people started investigating further what proton is made of? What made it so special that people started thinking of, oh, proton is not a fundamental particle. It can be further divided.
Could I answer this question?
Yeah, please.
So the reason is that further dividing it could help explain how the universe was formed, because when the universe was actually formed, it started from a singularity point. So there must have been particles which were smaller than a simple proton, which led to the formation of energy. So I think that's why.
Uday, are you convinced with the answer?
Yeah, I think it sums it up pretty well.
Very good, very good.
Yes, that was a good answer.
Very good answer. So, Uday, would you like to ask some more question? What you have just spoke, because Uday, you must interact. Need not necessary to finish whatever we decided in one go. Maybe half also, but if you interact with them, then only their interest also will be there, because you guys have worked so hard, Uday. You, Devangi, and Panto. So I really want this to be, this to assimilate in these kids who are joining. So Uday, ask another one question from this, and then please go ahead.
I don't really have any questions, I guess. Yeah, can anyone talk a bit about the standard model? Like one thing that the standard model allows us to do, like what's one important feature of the standard model? Just in general.
Also answer this question.
Yeah,
go on.
So the standard model is actually, it gives us like all sorts of different particles which might be involved in the formation of the bigger particles we know. So based on the list, I can first of all see that there's a photon. So the photon is the particle of light. So like based on the hypothesis which was given and it was further proven. Then gluon is another particle which can be used to explain gravity, but again, it's not been proven yet. And a lot of other particles here are classified on the basis of their spins, if I'm not mistaken. So like the fermions over here, they all have a half integer spin. So every single particle has been classified based on observations conducted on a subatomic level. So that's all I know about the standard model.
All right. Yeah, I think that's a pretty good answer. I think you preempted a bit of what we're about to cover. So I think we can move on now.
Yeah, I think we should move on.
Yeah. So thank you for that answer.
Also, I have one question. So like, I'm not sure if there was a session conducted last week, because I actually just realized that I got a mail from you regarding the change in links. So like I'm unsure where the original link was because I cannot find it in my inbox. So.
Oh, is that the case? I think there may have been an error because I think a lot of people, for some reason, did not receive the link, even though I sent it with the same mailing list. But nonetheless, like I'm glad you eventually received it. And last week there was a session, but it wasn't a live session. It wasn't like an interactive session. So if you want to watch it, it was streamed live on YouTube. So you can go on the Nucleus website and you can access the session from over there, and you can watch it if you want to do that, if you want to catch up.
But otherwise, the interactive sessions will be held from this link from now on.
So we'll have to decide. Yes, by default, you can assume that they will be held on this link. If not, it will be communicated to you via mail.
It's either this or Google Meet. So
yeah, Google Meet, because this is creating.
Right. Okay.
Yeah. So we'll if there's a change, we'll let you know. All right. Are there any more questions, or should we move on? Okay, I guess we can move on. So let's talk a bit about quarks. So one thing that I want to mention is the major differentiating factor between all these fundamental particles is what we call spin. Okay, I think one of you mentioned that just now. The spin is basically an intrinsic property that every fundamental particle has, and it's a bit tough to explain. So we'll be covering that in the next session. So for now, we'll be going into more qualitative properties of these different fundamental particles, and maybe in the next session and consequent sessions, we'll pay more attention to what spins are and try to differentiate these particles based on spins. All right. So let's talk a bit about quarks. Okay, so quarks are the first family of the standard model. They come in 6 variants, and scientists can be they can be a bit peppy sometimes. So they like to call quarks the quarks variants flavors. So you can say quarks come in 6 flavors, which are up, down, top, bottom, charm, and strange. Again, you can see the peppiness in the naming as well. Physicists like to have fun with their names. So these are the 6 types of quarks that exist, and these quarks basically have certain properties that differentiate them from all the other particles, right? So one of the most important properties that the quarks have is that they can interact with all 4 of the 4 fundamental forces, which we'll discuss later on. So they're the strong force, weak force, electromagnetic force, and the gravitational force. So quarks are the only family in the standard model that can interact with all of these fundamental forces, which differentiates them from leptons and bosons, right? Then all the other and then all quarks are electrically charged, and they either contain a charge of plus 2 by 3 or minus 2 by 3, negative 2 by 3. Now you may be wondering, how can something have an integer charge, or how does this work? Why are there fractions involved here? And it's a little complicated, but you can think of it this way. If you imagine a proton to have a charge of positive 1, right? So that's what you've been taught as well, that a proton is positively charged and it has a charge of approximately positive 1, right? So a proton is made up of 2 up quarks and 1 down quark, right? And scientists were basically looking into this, right? They were trying to figure out how do these constituents give rise to the electric charge in a proton. And they eventually found out that all the up quarks have an electric charge of plus 2 by 3, and all down quarks have a negative charge, have a charge of negative 2 by 3. So what do you have when you add 2 by 3, 2 by 3, and negative 2 by 3? You have positive 1. And that's how the proton gets a charge of positive 1. So by looking at the quarks, scientists were able to figure out why the proton has a charge of positive 1. Similarly, you can also explain why a neutron has no charge. It has a charge of 0 coulombs. So does anyone want to have a go at it? What if so? As I explained, I'll give you a hint. It's the neutron is only made up of up quarks and down quarks. It's not made up of other types of quarks. And all up quarks contain a charge of plus 2 by 3, and all down quarks contain a charge of negative 2 by 3. So what do you think a neutron is made of? So you know that a neutron is neutral, right? That's why it's called a neutron. It doesn't have an electric charge. Its charge is 0. So given I gave you this information that up quarks have a charge of plus 2 by 3, down quarks have a charge of minus 2 by 3, what do you think the neutron is made of?
I think there are some students who mentioned.
There
And
are
also, I would
many
like
students who are raising hands. So please see, Urjit and Siddhant, these two have already given answer, Uday. So please make sure that somebody who has not given. I'm sorry, Siddhant and Urjit, but
I actually had a question.
okay, so that questions you will come just after this. Somebody is raising hand for answer. So ask.
Excuse me, I would like to add something. There has been a small typing mistake. The charge is plus 2 by 3 or minus 1 by 3.
Yeah, minus 1 by 3. Yes.
That's supposed to be minus 1 by 3.
Oh, then my question is answered. That's the
Yeah, it's a typing mistake.
Yeah, bolo. Naman.
Yeah, sorry. So I'll fix this. Sorry about that. So yeah, does anyone want to answer it? What do you think a neutron is made of? So I can't see the names. Panthu, if anyone is raising
Yeah,
hand,
cool. Aditya, why don't you give a go to it?
Yes, the neutron is made up of one up quark and one down quark.
If it's one up and one down, then yeah, okay, go on.
You're not audible. I think there's some internet issue.
Ma'am, may I?
Am I audible?
Ma'am,
yeah, you.
Okay,
Yeah,
I
go on.
think we're not able to hear the first one.
Okay, so
Vaishnavi wanted to speak. I guess we can give Vaishnavi a chance. Yes, Beta.
yes, ma'am. Neutrons are made up of quarks. One is up quarks and two are the means down quark. And they are also made up of the particles like gluons, which means carry the interaction between the quarks.
So you've done your homework, haven't you? So yeah, that's right. The neutron is made up of one up quark and two down quarks. That's because when you add all the charges up, you'll understand that 2 by 3 minus 1 by 3 minus 1 by 3 gives you a total of 0, right? And that's why the neutron is neutral. And of course, you also mentioned the gluons, which are a bit complicated. So again, we'll go into that later on. But yeah, good job there. That's what a neutron is made of.
I had a question.
Yeah, go on.
I didn't exactly understand. Does the fraction 2 by 3 plus 2 by 3 and minus 1 by 3 specify mean? Does it mean the magnitude of the charge? I mean, how can you explain how to imagine a 2 by 3 charge and a negative 1 by 3 charge?
Okay, so usually we call electron a minus 1, right?
Yes.
But we also know that the charge of an electron in actual terms is 1.6 into 10 to the power minus 19 coulombs. So that's one way of saying. So that's the actual charge of an electron. So, but for easier communication and writing and all, it's considered as a minus 1. So, in this case, a minus 1 by 3 will be 1 by 3 into the charge of an electron. So it has an actual amount and it's not actually fraction, but because minus 1 is seen as a standard of electron, that's why these quarks who have charges less than the actual magnitude of the electron and proton, that's why they have a fractional charge.
Yeah, if you go into the actual measurement, they will still be in coulombs. So if you want to look at the actual magnitude of the charge, as Panthon also mentioned, you multiply minus 1 by 3 with the precise value of the charge of an electron, right? And you'll get a value which would be somewhere close to 0.333, and that would still be in coulombs. So that's still a normal magnitude. You can think of it that way.
Also, Ashish, I see you have your hand raised. Do you have a question? Anish, sorry.
Sorry, and now I don't have a question, but I just wanted to answer what is a neutron, but yeah.
Okay, it's okay. You'll get more chances.
Right, so should we move on?
Yeah.
All right, yeah. So quarks, as we just saw, quarks make up protons and neutrons, right? And as we discussed earlier, protons and neutrons are what make up like most of an atom, right? The protons and neutrons together exist to make the nucleus of an atom. So all the normal matter that we know, all the matter that you can interact with, the different states of matter that you know, are made up of atoms, and these atoms are made up of neutrons and protons, which are made up of quarks. So you can say that quarks are one of the most abundant fundamental particles in the universe, at least in not in the complete universe, but at least with the type of material that you interact with. Right?
Uday, 1 minute. I think someone has a question. Ashani, do you need to ask something? You have your hand raised.
I'm sorry, my name is Alia. I've actually joined from my sister's account. So I had a question about that. If there are so many types of quarks, which one is the biggest or the smallest in size?
Okay, that's a good question. So size and scale works a little differently when you talk about particle physics, right? When you look at quarks and when you look at all the fundamental particles here, more often than not, you would be discussing them in terms of mass and in terms of charge, right? Because we usually don't deal with size here because we're talking about such small scales here. Yes, probably if you Google it, you will find an answer, right? If you Google which is the biggest quark or which is the biggest fundamental particle, you will have an answer. But at that scale, first of all, those measurements are very hard to do. So we are not sure if those measurements are actually correct or completely correct, right? Or how precise they are. And secondly, at this scale, properties such as mass and charge play a stronger role. They play a larger role in terms of giving these particles the properties that they have, which is why we don't usually talk about sizes when we talk about particles here. So I don't know which quark is the biggest in size.
The heaviest is the top quark.
Yes, that's what I said. We can go into masses later on.
Yeah, the size doesn't really make sense when we talk about subatomic particles because according to quantum theory, there's no position. You guys will learn it later, but there is actually no position of the quark. So basically, and if you watch the last session, you would know in the electron cloud model, we described how the electron is not a ball or a particle. It kind of becomes a cloud-like thing, probabilistic cloud. So all these particles are also similar. So there is nothing called a size, like you can't measure diameter. But if we talk about mass, then top quark is the heaviest one.
Okay, thank you.
Wait, is mass proportional to charge on that particular quark?
Nope. All quarks have the same charge, that is either plus 2 by 3 or minus 1 by 3, but they have different masses. So your mass and charge do not correlate in directly. They don't correlate.
All right.
All right. So let's move on to leptons now. So leptons, I guess the name isn't as cool as quarks, but leptons are again very interesting particles. They're the second family in the Standard Model. And there are two types of leptons that exist in the Standard Model. First are the electron-like leptons. The most obvious property that they have is that they all have an electric charge. And then the second type of leptons are called neutrinos. You may or may not have heard this term before. So neutrinos do not have electric charge. You will come to learn more about neutrinos when we go into nuclear physics and stuff. But as of now, you can remember this, that neutrinos do not have electric charge, and just never confuse neutrons with neutrinos, okay? They're completely separate particles. Neutron isn't even a fundamental particle. So just keep this in mind. So again, like quarks, there are 6 flavors of leptons, and they're divided, again, as I mentioned, into these 2 families. Both contain 3 each. There are 3 types of electron-like leptons, which are the electron, the muon, and the tau. And there are 3 neutrinos, which are actually which correspond to the electron-like leptons, right? Now, the reasoning behind this is a bit complicated, but as of now, just remember this, that you don't have to remember it, but you can think of the lepton family in this way, that for each electron-like lepton, there's 1 neutrino. So you have 1 electron neutrino, muon neutrino, and tau neutrino. So let's talk a bit more about leptons. So as I mentioned, not all of them not all of them have electric charge, and all of them have different masses. So the electron is the lightest of all the leptons, and it's also the most stable. Now, you may be confused about what the word stable really means, and you can think of stable in a way that the electron can exist in more peace in very candid terms. So when we when we compare it with the atoms, for example, from the periodic table, we say that the noble gases are stable, whereas alkaline metals react a lot. They react with a lot of different things in a very aggressive manner, right? So you can think of, it's not a perfect analogy, but you can think of stability here in a similar way as well, that electron can exist in an independent way to a larger extent than muons or tau particles, right? And another very important characteristic of leptons is that they do not interact with the strong force. So from the 4 fundamental forces, they can interact with the electromagnetic.
Uday, we have 2 hand raises. Okay, so Anish.
Yes, so my question is that we say that atom is made up of protons, neutrons, electrons. So does this leptons come in electrons?
Yes.
Sorry?
Or something else?
Sorry?
Right.
They come in electrons as...
Yes, so I'm asking that does leptons come inside electrons, or is it like separate?
Electron is a type of lepton. Lepton is the category, like quarks was a category of particles. Lepton is also a category of particles. Electron is a lepton.
Oh, okay, thank you.
And an electron is actually a fundamental particle. So it, like, unlike protons and neutrons, which we now know that they are not fundamental and can be broken down into quarks. Electrons, however, are indeed fundamental particles for now, and they cannot be broken down into more particles.
Which class this child is who is asking question, Pantho?
It's Anish.
Anish, which class?
6 Ariska, ma'am.
I am so very much impressed. Look at your audience. I mean, I told you that student at any age can be ignited about pure physics. Please go ahead with it.
Vidush, you also have a hand raised?
Yes, I just wanted to ask, on what basis are we defining the stability of a lepton?
Okay, so stability you can understand like tau, mu and tau. These 2, they in a way are suicidal. They don't like to exist for a long time. So what muon and tau they do, they just break down into electrons and WZ bosons. We'll talk about that later. It happens because of the weak force. So basically, tau, if I remember correctly, is 500 times the mass of an electron. So it does not. And its life is about like a few microseconds. So it can only it can only exist for a few microseconds, and then it will convert into electrons and release energy.
Okay, thank you.
Should I go on?
Yeah.
All right. So I was saying that leptons do not interact with the strong force, right? So out of the four fundamental forces, quarks interact with all of them, whereas leptons interact with three of them, and they do not interact with strong force in any way, which differentiates them further from the quarks. Now, another differentiating factor, again, I'll reiterate that, is the spin, right? But as I mentioned, we'll go into spin in the next session. So as of now, you can think of the leptons as a particle that contains charge and it does not interact with a strong force. And a very good way to remember leptons in your memory is that electrons are leptons, right? So electron is one of the most abundant particles in the universe. It's the most common lepton in the universe. And again, all the matter that we know is made up of atoms which contains an electron, and each electron is a lepton. So you can see the importance that leptons have in creating the matter that we know today. Lastly, I'd also like to talk about gauge bosons. So gauge bosons are known as the force carriers. Okay, so I mentioned earlier that the standard model allows us to explain how forces interact, right? They allow us to explain how forces, how we can exert a force, right? All of the fundamental forces. I explained that with the example of friction. So we do that with the help of gauge bosons. Now, for three of the four fundamental forces, we have particles that explain the mediation of these fundamental forces. So first, for the electromagnetic force, the details of that Panthu will explain later on, are mediated by photons. The strong force is mediated by gluons, and the weak force is mediated by W and Z bosons. So in a way, these particles form the bridge between other particles, right? So you can think of it this way: that let's say a quark and a quark want to interact with each other using the strong force, right? So how do they do that? They take the help of a gluon, and by doing that, the gluon mediates this force and allows the quarks to interact with each other using the strong force. So in a way, you can think of these quarks as your phones.
I think someone has a hand raised.
Yeah, I'll just
take questions after that. Yeah, somebody is raising hand.
Right, so I'll just finish this slide, and I think after that we can take questions beforehand.
Uday, today's session, since you are taking slowly and interacting a lot, is going on well. And okay, we'll discuss with Panthu and Devangi for next session, more interaction, how can it take place. Thank you. Please carry forward.
Yeah. So as I was saying, you can think of the quarks as your phones and your gauge bosons as your telecarriers, your Airtels and Vodafones. So they allow these particles to interact with each other using these fundamental forces. Now at high energies, these W and Z bosons, along with the photons, sort of start working together, and they form the electroweak force. Now, this is something which is a bit more complicated, but I thought I should mention this because it becomes important if you decide to study more complicated particle physics later on. And one question that some of you may have had right now is that gravity is one of the four fundamental forces. So what about gravity? Where does gravity fit in? Which gauge boson explains gravity? And right now, it's one of the biggest mysteries in physics, right? Because we don't know we don't know how gravity exists and which particle is responsible for gravity. There was this person called Albert Einstein who gave the theory of relativity that explains gravity in a completely different way that does not require a particle to exist at all. But there are a lot of particle physicists who say that there may be a particle called graviton that may exist, but it's very difficult to detect, which is responsible for mediating the gravitational force. And it's still a theory. So we don't know for sure if the graviton as a gauge boson still, if it exists or not. We don't know if it's a particle that, we don't know if a particle is even responsible for the gravitational force or not. But right now, graviton and the theory of relativity are so you can say the two leading theories that explain the existence of the gravitational force. Now, like the last particle, the last family is the scalar bosons, which is basically the Higgs boson. And since it's a very interesting and a very rich topic, I won't be covering it right now. So if anyone has any questions right now, maybe Devangi, you can ask them to go ahead.
Yeah, someone has their hand raised. You can unmute and ask a question.
May I ask?
Yeah, go on.
My question was, what is the difference between positive and negative particles? I did not understand that.
Like the charge.
Yes.
Okay, so charge is basically another property that particles have. It's like mass. Like there can be positive mass. So it's very similarly, there's a property called a charge, which can be either positive or negative. So there's it. A more like this is the simplest way we can describe it right now. If you want a more complex one, then we have to go into the whole realm of quantum field theory.
If I may just add, when we say positive and negative, primarily what we are saying is that the negativity, it behaves, in the opposite way the positive one behaves. It's not exactly zero say come. When we say negative, it doesn't mean less than zero kinds. It's basically, when we talk of the north and the south pole, basically, if you look at it, the south pole is going to behave, it's going to act opposite like that of the north pole. So when we say positive and negative charge, this is exactly the idea. The behavior is going to be opposite of each other. Was that helpful, Beta?
Yes, thank you so much.
Siddhant?
Yeah, I had a question. So like a lot of scientists have not been able to connect the gravitational force with the nuclear force, saying they're quite different. So can subatomic particles be, used as a basis to relate them in a way? Like,
relate them in a way
as in, find out the similarity between them, because both of them act as attractional forces. So
there's one thing, like when we discuss the fundamental forces, I'll talk about it. Strong nuclear force is not always attractive. It is both it's repulsive in short distances and attractive at larger distances. So no, actually strong force and the gravitational force, like they tried, but it does not seem like they'll be like it's not a very easy fit. And the reason for that is like the strong force. Uday, can we go to the next slide? Then I can start. Then I can talk about the relative strength. So basically, the strong force is like in when we talk about relative strength, we consider strong force as one, like keeping other things constant. We just see like how strong these are. So the strong force has a strength of 1. If the strong force has strength of 1, then gravity, as you can see, has a strength of 10 to the power minus 39. So in comparison to the strong force, gravity is very weak. And as you can see from this slide, the gravity is actually the weakest of the 4 fundamental forces. And then the second number, we get the electromagnetic force and then the weak nuclear force. So no, you can't you can't join the strong nuclear force and the gravitational force together to get a unified theory.
Oh, all right. So the unified theory is okay. I got that.
Very interesting discussion going on right now. And no matter these kids, if they understand all this at this level, I don't know, sky is the limit for them. They will further research, they will further come back, and so thank you children for being so actively participating in question answer session, all the audience. So there is another question by Anurag Singh. Please go ahead, Anurag.
Can we share the slide in a group?
Sorry, your voice is not very audible. Can you repeat?
Can I get the slide?
Can you type in the chat box? Maybe we can't hear you.
I think so he's asking about cloud something. Can you write in chat box, bacha?
And there is not in chat box.
There's no chat box?
There is chat box.
Okay, can you speak loudly?
Yes, ma'am. And the slide can be shared with us.
Your voice is not clear. So can you please write this question in mail? Our mail is right now open. So I will read that question for Uday, Pantho and Devangi. So can you just write this question, the mail what you got in that, and you can write to Uday, you can write to me, anyone, Pantho or Devangi. So any other questions? Any other question, Anurag? So till the time he he's writing in mail, children, is there any other question? I really got excited when I was a kid and I was in, college. And obviously these were not taught in school time. And I heard about strong and weak forces and, electromagnetic forces, etc. And this is something very interesting that, the way these kids are explaining you and you guys are engaged in, in this discussion. The strong force, how it is distance, dependent and very strongly distance dependent, and how it is attractive when it is a little bit far away, and how it becomes repulsive when it comes closer, or how it is, all those things. So, and that is the reason for this exists inside nucleus, the stability of nucleons inside nucleus. Can you please speak a little bit about that, Pantho, that how this strong force is responsible for, stability of nucleus for another 1 or 2 minutes?
Yeah, yes, ma'am. It's in the next few slides only.
Okay, so there is a question by Arnab. Please go ahead, Arnab.
I had a question in general. Is there a specific reason why the strength of the gravitational force is so low relative to the other fundamental forces?
That's actually one of the questions in the whole particle physics field that is not quite answered yet. I don't know if you have heard about it, but there's the whole string theory. It's there to describe why this is, like the string theory, the M theory, or even quantum gravity as a theory. It's there. They're all trying to describe why gravity is so prevalent, but also why is it so weak. So, and again, because of whole Einstein's general theory of relativity, it's a lot of scientists have have a lot of questions regarding gravity as a force. So that's why, like all the other forces, they have defined bosons, they've defined things, but for gravity, a lot of things are not known when we go into more deeper. And also. And also the another reason there might be the gravity force might be very weak. That is, if gravitons do exist, then they'll have to be very small because they also affect photons. Like, you may, yeah, go on.
So I think Anurag was asking some question, but his voice was not clear. Anurag, did you write mail to us? So you can always write by mail, and please remember, or Uday will write a mail and ask question. Your voice was not clear. Over to you, Uday, Devangi and Pantho.
Okay, so coming back to the slide of the fundamental forces.
Yeah, just a second. My internet is being a little problematic, so is it possible for you to share your screen to show the slide?
Cool. I'll do it.
Also, Pantho, because the students are of different age group and they are pretty young also. So what I suggest, if you want to go, more slow, please go.
Okay.
There is no hurry in covering all modules, which maybe some of the module we will take again in October or some other break. But go as slow as possible. Let it be as interactive as possible. Okay, And
Okay.
also keep a time in mind. If you feel that it's 1 hour and you want to wind up, and you can take this, because this recording of 1 hour will go on website, and you can take session in next this thing. So please keep all those in mind, because more than 1 hour, the attention spans drops. Thank you. Over to you.
Okay, so yeah, so where were we? Yeah, fundamental forces. So fundamental forces govern how objects interact with each other and how certain particles decay. We'll talk about particle decay in the next few slides. So all known forces of nature can be traced to these four fundamental forces. For example, Uday talked about friction. Now, friction is a derivative from the electromagnetic force. Friction comes
One,
about.
someone has a question, I think.
Yeah, go on.
Can you unmute and ask?
Yes, I just wanted to ask that how do these fundamental forces like govern how the objects interact? Like how do they?
How do the objects interact with the fundamental forces? Is that your question?
Yes.
Okay, so we'll tackle each fundamental force one after the other, and there I'll explain how the particles interact with each other. Okay, so is this slide visible, right?
Yeah, it's visible.
Okay, so first we move to the electromagnetic force. It explains how stationary and moving charged particles interact. So I'm sure you guys are now know what charged particles are, right?
Yes.
Okay, cool. So every charged particle gives off an electric field. Electric field is basically for example, a positive charged particle. It at it attracts all other negative charged particles towards it and repels all the positive charged particles. So that's just that. So that's an electric field. So it's basically like a magnet. Where in fact the electromagnetic force is also the reason why magnets work. A magnetic field originates only in moving charged particles. So like when a charged particle is moving, that creates a magnetic field. So the electric field and the magnetic field are actually part of the same fundamental force. So this force keeps the electrons in their orbit around the nucleus, and the carrier of this force is the photon, which is light. Any questions till now? Or something that I should go deeper?
I had a question.
Go ahead.
As you just explained that um, the nucleus keeps up with the electron, basically keeps the electrons in place through the electromagnetic force, correct?
Yeah.
Yeah. So, and we also discuss. You just also said that the carrier for this force is the photon. So, what place does the photon stand inside the atom? Because it should exist, according to me, if this force is being exerted between two objects.
Okay, so photons basically move inside. They move around the. Also, am I visible? Okay, so basically inside the atom, the photons bounce back from the nucleus to the electron, and the whole point of chemistry and like this things called excited state. So if you add if you give if you pass photons through an electron through an atom, so a lot of times what happens, the photon gets absorbed by the electron and it can move away from the nucleus. So basically the photons, they keep bouncing back from the electron to the nucleus, and that's how it keeps the orbit in check.
So does the electron or the nucleus radiate this photon, which helps it bounce back, because it should have been because it would have originated from somewhere.
It originated from the excitement of the electromagnetic field. So that's again a bit higher in the quantum field theory concept, but it keeps bouncing, and the reason and the whole point is that electrons cannot exist beyond like there's specific shells, the specific energy levels where the electrons can exist around the nucleus. So that's why, and what you said was exactly right, that it should ideally decay, right? The whole point of Rutherford's model not working out was this only. So Niels Bohr, his atomic model, told the world that the electrons do exist. It only exists around specific energy levels, because on those levels the photons can just bounce back from the nucleus to the electron, and they keep sharing information. So when the atom was formed, that time these photons got trapped inside, and they don't have to go out of the atom unless external force or external interventions, basically.
Can I also add Pantho here?
Yes, ma'am.
So what he has explained, Pantho has explained he has explained very well. So you understand like this. See, when nucleons came together, they formed nucleus, right? And when they formed nucleus, then all nucleus came together. There was some interaction between proton, neutron, etc., which was charged. In that interaction was charge independent. And during the formation of nucleons, when these protons and neutrons came together, obviously some of the mass, net mass of the nucleus got converted into energy, and that is responsible for binding the nucleus. Point number one. Point number two, let's talk about orbit. When the electrons are revolving in the orbit, as Pantho said, that Niels Bohr said that there is a specific orbit in which one electron can revolve. They have a specific orbit, so please understand this. They cannot just move, move in any orbit. And in next class, Pantho obviously will speak about it, that how this how this orbit is chosen for that particular electron. This is very important. Okay, so if that electron has to go to the next orbit in excited state, obviously it will absorb some energy and go to the next stage. But it cannot stay there for longer time. It has to come back. So it will come back again, and that photon, when it goes up, it absorbs photon. When it comes down, it releases photon. Now this photon is again captured by another electron, so it goes to the other one orbit, it comes back, and this phenomena keeps taking place. So electrons, obviously they jump from one orbit to other orbit, absorb photons, go there, come back, release photon, and these photons are again, so there is no loss of energy as such. This is just exchange between the orbits. Okay, so is your doubt clear, child?
Yes, ma'am.
Thank you. So we'll, Pantho, may I request, because such an interesting, I to feel like going. Maybe we have to take few more sessions, but if you see that time is up, just give a nutshell of what you have done in 2-3 minutes, and we'll connect again in the next class, because more than 1 hour the children span, they can't concentrate more. But you must, before wind up, Pantho, you must revise everything in just 2-3 minutes. Also, tomorrow's session, or I don't know when is it, Uday must be knowing, Pantho, is very interesting, because obviously this session also many things are left. Along with that, Devangi is going to introduce particle accelerator, which nobody should miss. Okay, so which is going to speak about particle accelerator and Higgs boson, etc., and how the particles are accelerated. So over to you, Pantho. Thank you.
Okay. So I'll do a quick recap of what we learned today. So in the standard model, there are 4 basic types of particles. There's the quarks, which have 6 flavors: up, down, top, bottom, charm, strange. These quarks are the only particles which experience all 4 fundamental forces. These quarks have a charge of either plus 2/3 or minus 1/3. Combination of quarks, two or more, when 2 or more quarks combine, those particles are called hadrons. Then there's the leptons. There are basic 2 types of leptons. One is which contains the electron, muon, and tau, and the other are the corresponding neutrinos. So electrons, all the electron muon and tau, they all have a minus negative charge, and electron is the lightest and the most stable lepton, and they do not interact with the strong force. Then we get the gauge bosons. They are the force carriers for strong, basically force carriers for fundamental forces. There are four types of gauge bosons: photons, which mediates the electromagnetic force; gluons, which control the strong force; W and Z bosons, which mediate the weak force. So at high energies, and also in the early stages of the universe, when the Big Bang was pretty young, and there were no particles because like it was too hot. That time the photons, W bosons, Z bosons work together to create the electroweak force. So that force then got split into the electromagnetic and the weak force. Then we have the relative strength of fundamental forces, where the strong force is the strongest one, and it has a range of about 10 to the power minus 15 meter, which is around the diameter of a medium-sized nucleus. The electromagnetic force, which is the next strongest one, and it has an infinite range. The weak force, which is after the electromagnetic force, and it is the least ranged force, which is around 10 to the power minus 18, which is 0.1% the diameter of a proton. Then we have the gravitational force, which has an infinite range, but has the least strength, that is 10 to the power minus 39. Then the electromagnetic force. This basically this basically tells us how charged particles moving or unmoving charged particles move. We'll talk more about, we'll watch more videos, we'll watch 2 videos about the electrostatic force and discuss more about the fundamental force in the next session, along with Debangi will take on the concept of particle accelerators.